So we were discussing regarding the analysis and design of machine foundation, and especially for foundation of reciprocating and impact type of machines. So we saw that to design the machine foundation, so we have the static loads from the machine, and when the machine will be operated, we will have the dynamic loads. So the thing is that the soil behavior, it should be within the elastic range. So that is important. Or what will happen is that the plastic deformation, it will accumulate with the operation of the machine, and it may lead to settlement or deformation which is unacceptable. And then the amplitude of the motion, it should be within the permissible limit. We have seen that. So we should be able to control the natural frequency of the foundation system so that all of this criteria is fulfilled. Okay, that is our main objective. So our objective is to arrive at a natural frequency of the system which controls these particular behaviors. So we saw that there are various types of machines. So reciprocating machines and then impact type machines. So rotary machines, there the frequency of operation is very high and the dynamic loads are comparatively lower than reciprocating and impact type of machines. And in the impact type of machines, we saw that it is the dynamic load is significantly higher than the reciprocating machines, and it is not like the reciprocating machine. So the loading conditions for the two, so we can approximate the reciprocating machines to be of sinusoidal nature, while in the impact type we have suddenly there is an impact and then there is the response of the soil and it stops. Then again suddenly there is an impact and there is a response of the soil and it stops. So in that way the impact type machines behave. So this is a loading condition for the various types of machines. So this is what the reciprocating machines generally behave like, and this is what the impact type of machines generally behave like. So we have a sinusoidal nature and we have one impact and then the response of the soil, then another impact and the response of the soil. So we saw that we have to fulfill two criteria. First of all, the static loads from the machine. So the foundation system, it should not fail in shear failure or it should not settle excessively. Alright, so this is the general foundation system criteria. So all the general foundation, whatever the criteria is there, that has to be fulfilled for the static loads, for the machine foundation as well. Apart from that, we have the dynamic loads. So when the machine is operated, what will be the response of the foundation and the machine system as a whole with the soil, along with the soil? So that has to be assessed, right? So the thing is that there should be no resonance. Amplitude should be within permissible limit and it should not cause annoyance to the persons working there and the precision instruments like the gauges, pressure gauge, alright, dial gauges, time measuring instruments, alright. So all of that should not be hampered. So we saw that there is a particular limit, we have to be within that, and if possible we have to be within certain limits so that it does not cause any annoyance to the persons working there. So we saw that there are two methods of analysis for machine foundation. One is in which the soil on which the foundation is laid, it is approximated as a series of spring or as a spring. Alright, so we assume that it is consisting of linear weightless spring, and the behavior is then analyzed based on that assumption. So the soil is assumed to be composed of spring. And the second method is based on the linear theory of elasticity, that is elastic half space. So the soil is thought of to be composed of an elastic half space. So this is the surface of the soil, and on top of this we have the machine foundation and bottom. So this soil, it extends in x, y and negative z direction, in the downward direction to infinite lengths, and we have this surface of the soil. So that is elastic half space, that is what. So we will definitely come into that if time permits afterwards. So we saw that there are 6 degrees of freedom for a machine foundation. translation along z-axis, which is called up and down the motion. Alright, then the rotation along the z-axis, which is called the yawing. Then we have the translation along the y-axis, okay, right and left motion. Then we have the rotation around the y-axis, which is called the pitching, alright, or the rolling, whatever you say. So we have done this along the x-axis, translation along the x-axis, and rotation along the x-axis. So we have 6 degrees of freedom. So these are the degrees of freedom. Now we also saw that these two types of motion, right, they are similar in nature and their behavior and response is also similar. Right, and they are generally coupled. We will see how they are coupled and how they are coupled in maybe in this class or in the next class. And then we have the motion along the z-axis, the translation motion, and the rotation along the z-axis. So these are the 6 degrees of freedom. Obviously, analysis of these two motions, of these 4 motions actually, they are of the same nature. So we have basically 4 modes of vibration, 4 modes of motion. So one is this translation. So this is called the uniform compression. So when this motion occurs, this foundation, it is uniformly compressed in the entire area. So we call it uniform compression. Then we have the uniform shear. So either this entire foundation is moving in this direction or it is moving in this direction. So it is going in this direction or this direction, and it is in this direction. So x or y direction, ultimately both is same. So that is of uniform shear. Okay, so the entire foundation, it is uniformly shearing the soil in either one direction, either this direction or this direction. And if we consider the y-axis, x-axis, so either in this direction or in the opposite direction. So uniformly shearing. So that is uniform shear. Then we saw that when there is pitching and rolling, so it rotates about a point. Alright, so the compression along one direction is more and in the other direction there may be tension. Alright, so there is non-uniform compression. So when this was acting, when the foundation was moving along z-axis, it was uniformly, the compression was applied uniformly. Now when it is rolling or pitching, we see that the compression is not uniform. It is more on one side, there is compression on one side and there is extension on the other side. So we have this motion. So there is extension on this side and there is compression on this side. So and there is a rotation of the foundation. So that is why it is called the non-uniform compression. Then we saw that if the foundation, when there is a rotation about the z-axis, okay, so if this is the foundation and this is the z-axis, and if there is a rotation, so if we draw an axis, so when there is a rotation, that axis will rotate like this. So we see that when there is the soil at the bottom, so we have this suppose axis and it will be rotated to this direction here in like this. So all the soil will be rotated in this manner. Okay, so we have this foundation. So that is why it is. So the shear is more radially outwards. So if we come outwards, so shear is more. If we go inwards at the axis, it is almost negligible shear. So that is why it is non-uniform shear. Okay, so there are 4 modes of vibrations. Now we have to analyze the foundation system. Basically how the foundation system will move. So we start from the vertical vibration of the block, so uniform compression. So the soil, it is assumed to be composed of spring, and ultimately we can approximate this entire system to be of this manner. So we have a spring and we have a mass and we can consider the downward direction to be positive. Alright, if we rotate it up, so it will be of this manner. So the spring will be like this and the mass will be, so this is the positive direction, upward direction. Okay, so downward direction we can consider positive. Anyway, so we have to now analyze this system. So before going into analysis, I thought we will just refresh what we have learned for the analysis of this simple harmonic motion. Okay, and especially how we can obtain the phase diagram, because that is very important to understand the concept of the motion. Alright, so first of all, so we have this spring, so the soil, that means we have the soil and it is unloaded. Alright, so we have the soil and therefore there is no deflection in the soil. Then suddenly we place the machine foundation on top. So as soon as we attach the machine foundation, what will happen? This spring, it will extend down. So this is now the equilibrium position. So this is delta static. Okay, so we can define delta static is equal to, so here K into delta static, so that is the force in the spring. Alright, so when we will extend the spring, there will be force generated, so there will be a force in the spring. So the spring will pull this mass upward. Alright, so that will be equal to K into delta static, whatever is the displacement. So we know that when there is a spring, so if there is a spring and there is a compression in the spring of X, then the spring exerts a force of K into X, where K is the spring constant. Okay, so similarly here also K into delta stat, it will pull up. Whereas we have the mass, so weight will be there, mg. Alright, weight equal to mg. So delta static will be equal to this K into delta static will be equal to W. Alright, so delta static will be equal to W by K. Okay, so that is the equilibrium position now. So when we consider the harmonic motion, we will consider this to be Z equal to 0. Okay, so we will consider this to be Z equal to 0. So I think this is clear. Right? So now we move on to this. So somebody holds this mass. So somebody holds this mass and it pulls, the person pulls the mass down to a displacement of Z max. Right? So he pulls the mass to a distance of Z max and he releases it. Now when the person will release, now additional force, total force on this mass, what are the forces? So we have weight, now the person has released, okay, whatever force he has applied to pull the mass up to this position, it has been released. So now at this instant, what are the forces? So we have W, then we have K delta stat plus Z max. So total displacement is delta stat plus Z max. Okay, so that is the total force. So equal to, and then W in the downward direction, so minus W. So this is a total force. So now what will happen is that the mass will accelerate upwards. So the mass will accelerate upwards. So we know F is equal to ma. Okay, so the person pulls the mass downward up to a distance z max and he leaves it, releases the hold. As soon as he releases the hold, the spring will pull the mass up. Okay, the spring will pull the mass up. So the mass will accelerate. So that is the acceleration ma. So we know F is equal to ma. So what are the forces acting? So we have W, downward direction, and we have K delta step plus Z max in the upward direction. So we have K delta stat plus K Z max, okay, minus W is equal to M into A. Okay, so now K delta stat and W cancels out because they are equal. So what is the force remaining? So we have K into Z max. Okay, so that is equal to the acceleration, mass into the acceleration in the body. Okay, so if I have to now what will happen? As this mass will move, now the spring will exert a force, so the mass will go up. Okay, so when it will go up, the displacement will reduce. Alright, so we can, for that time, alright, so we can generalize this equation. Now this Kz max equal to ma is at this point. Alright, so when it is at maximum displacement. When it is at a distance of z, okay, so then also the acceleration will gradually reduce. Okay, the acceleration will gradually reduce. We will see that also. So we can generalize this equation. So what we can say is K into Z, which is the force applied by the string on the mass, so equal to double differentiation of the displacement, alright, or m into a, that is. So ultimately we can say Kz minus mz is equal to 0, or this particular positive or negative sign, it can be ultimately, when we will do the analysis, or when we will do the calculation, it will ultimately be taken into consideration. So ultimately we can write an equation of this sort. So one is the acceleration in the body, mass into the acceleration, alright, then so this is the inertial force. Okay, so this is the inertial force, so that plus force from the spring is equal to 0. Ultimately plus or minus whatever it is, it will be taken care of. Okay, so thing is that we have to first understand that when this is the spring, when the mass was loaded, so the spring, it extended up to this condition. Now this is so initially this is the condition of the spring. So now this is the equilibrium condition, static equilibrium condition. Okay, static equilibrium condition for the mass and the spring. So we have the spring force K delta stat, and we have the weight in the mass, alright, pulling it down, that is W is equal to mg. So this is the static equilibrium. Now suddenly somebody pulls this mass to a maximum displacement of z max. Okay, to a maximum displacement of z max, and then it releases it. Okay, so he then releases it. So at this condition, so we have K into z max acting from the spring upward, and we have the weight mg acting downward. All right, and we have k delta stat acting upward. So these two forces will cancel each other. All right, and then we have the acceleration in the mass ma. All right, so ultimately we have force is equal to mass into acceleration in the body. So this is the inertial force. All right, and that will be the opposite to the force which is applied on the body. So now what will happen is that this body, this mass, it will oscillate between this equilibrium condition. So this is the Z max. Similarly, it will go up to Z max. Again, it will come down to Z max. Again, it will go up to Z max. All right. So it will start oscillating. Okay. So at any point, we have the mass into acceleration of the body plus the force from the spring is equal to 0. So this we can write double differentiation of the distance. So we have distance, so dz by dt is the velocity. So this is written as z dot, and d square z by dt square is equal to acceleration. We have double, right, plus kz is equal to 0. So this is the forces on the body. Okay, inertial force and the force applied by the spring. So we have this mass rotating, so we have the spring constant k, and ultimately what we can do is we can approximate the motion of this mass with this equation. Alright, or we can also take a sinusoidal equation. So a is the maximum amplitude or maximum displacement, that is the amplitude. A is the amplitude, and cos of omega t minus phi. Now phi is the phase at which you start. So suppose t, you start at some point and when the displacement is at that point. Okay, so from there it will be like this. Okay, so this is the phase difference phi. Now in this case it is starting from here, so phi is equal to 0 in this case. Okay, similarly we can also approximate as a sine curve. So sine omega t. Okay, same as this one, sine omega t. So here also we have the phi, it is starting from 0. So the phase is 0, the starting point. Now before going to draw the phase diagram, we have to understand how the particle moves or the mass moves. Alright. So first of all, let us concentrate on the displacement. So this is the equilibrium displacement, z is equal to 0. Okay, and when the mass moves, so the displacement z, it increases, alright, increases and then increases up to the z max. Okay, so variation of z, so it increases in the downward direction, then again it comes back, so this is again 0 position, then again it goes up, so this is again z max. So this is negative, we can say, and this is positive if we say. Now what about the acceleration? Now when the mass is at the maximum displacement, so it is experiencing the maximum amount of force. Okay, so this force, it is maximum here. So k into z max. As the displacement decreases, as the mass goes up, all right, so the force also decreases. So as the force will decrease, the acceleration will also decrease, because we have kz is equal to mass into acceleration. Okay, so acceleration will be maximum here, and it will decrease in this direction, and it will be 0. Again, when the particle will go up, now the acceleration will increase and it will be towards this one. So you see, z factor is directed away from the equilibrium position, away from the equilibrium position. So displacement is increasing away from the this one. Okay, mass is also increasing, but sorry, not mass. Acceleration is also increasing, but acceleration is always directed to the equilibrium position. Okay, so that is why the phase is opposite. Okay, if we have z in this direction going, so as the z will increase, the acceleration will increase in the opposite direction. Alright, so the acceleration will increase in the opposite direction. So we have this phase. So this is displacement, and this is acceleration. Okay, so as the mass will move down, the acceleration will be increasing upward. So acceleration is always directed towards the equilibrium condition. Alright, and then obviously the velocity. As you see, the velocity is 0 over here. V is equal to 0 at this point. At the extreme point, the velocity will be 0. Okay, and then when it will come to the center, the velocity will increase, and the velocity will be the maximum at this center. Okay, and then again it will reduce because the acceleration is in the opposite direction. It will reduce, it will become 0 at the extreme point here. Then it will change its motion, so now it is coming down, so it will reduce, it will stop, velocity will stop. Then again the velocity will now increase in the upward direction, so maximum at this point, and it will shoot up to this position. So as it will go up, acceleration again in the downward direction, so the velocity will reduce, it will be 0 at this condition, it will stop, then it will change its direction of motion, it will again come back. Okay, so this is displacement, this is acceleration, and we have the velocity in this direction. Okay, this is the phase of the velocity. So this is very important, because it becomes easy to analyze simple harmonic motion based on this concept, the phase diagram. Okay, so we have xt, or the displacement, function of time, as we can approximate as cosine function or sine function. Alright, so if we have a cosine function, and for our case, suppose we consider the phase to be initially 0. Okay, so if we consider 0, so we can neglect this. So if we differentiate this, we will get the velocity. So we see that it is at a phase difference of pi by 2, that is 90 degree. Alright, mathematically as well. So if we double differentiate or differentiate this velocity, that is, alright, so we will get again, so this is the acceleration, and we will get a phase difference of 180 degree or pi. Okay, so that is the acceleration phase. And what about the amplitude? So amplitude of the displacement is z, that we know, because here the amplitude was given, that is the z max. Alright, so that is the z max which was given, so that is the amplitude z, here capital Z in this case. Now when we differentiate it, so we have dv by dt, dz by dt is equal to dv, v velocity, alright. So when we differentiate, omega n will come out. So here you see this is the cosine function and this is the maximum value of the velocity, z omega n. Alright, so that is the maximum velocity of the particle. Alright, so that is the maximum velocity, value of the maximum velocity. So that is the amplitude of the velocity phase, we can see. Alright, so this is the amplitude of the displacement and this is the maximum velocity. Now if we again differentiate this velocity, we will get, again this is the cosine function at a phase difference of pi by pi, that is 180 degree, and we have this maximum value of acceleration. Okay, so I hope you have understood how it is happening. All right, so when there is a particle, so it is stopping at this point. All right, so it is stopping at this point and the velocity is increasing up to this point. Then again it is stopping at this point. All right, and then again the velocity is increasing at this point. So the velocity is maximum at this point. But what about the acceleration? Displacement is obviously zero at this point, we know. So if it goes down, displacement will increase. If it goes up, displacement will increase. So this is the displacement and this is the displacement. Now what about the acceleration? So when it will go down, the force will increase proportional to the displacement. Okay, so when it will go down, the force will increase proportional to the displacement but in the opposite direction of the motion. Okay, so the acceleration is always directed to the center. So when this particle is going down, the acceleration will also increase but in the opposite direction. So it will increase in this direction like this, right, in the opposite direction. Okay, so acceleration will increase in the opposite direction, that is. And the velocity, it will be maximum at the zero displacement points. Okay, so we have this velocity, so it is maximum here. Okay, then zero at the maximum displacement, then again maximum at the zero here. All right, so zero displacement. So that is how the velocity will change. Okay, so that is, we have, if we have x in this direction, we have the acceleration in the other direction and we have the velocity in the perpendicular direction. All right, and we have this magnitude of the maximum velocity, maximum acceleration and maximum displacement. And obviously we have the time period, we have the frequency, all right, and we have the natural frequency. So now we have arrived at the phase. So we have the displacement in this direction. So as the displacement will go increase downward, the acceleration will increase upward. All right, and at this point it will be the maximum acceleration upward and the velocity will reduce to zero. Okay, and the velocity we have in the phase difference of pi by 2. Okay, and this is the acceleration. Now what about the force? So this is displacement, this is velocity, and this is acceleration. Now what about the forces? So we know spring force, it is K into Z. Okay, so definitely it will be opposite of the displacement. So K into Z. So we have K into Z. So this is the spring force, opposite of the displacement. Now this is the acceleration, A, and we have the inertia in the opposite direction. Alright. So F is equal to ma. So we have always the inertia in the opposite direction. So we have the inertial force in the opposite direction. So that is m into omega square into z naught. Okay, so this is acceleration A. Right, so we have the force factors kz naught, right, kz naught, and m into omega square z naught. Okay, now we know, so if there is a despot, all right, so if now we have considered only a spring mass system, and we have also discussed that if there is a damping here, all right, a despot here, and this is the c is the despot coefficient, so this force will act always opposite to the velocity. Okay, and it is proportional to the velocity. As the velocity will increase, the force against the velocity will also increase. So that is what the despot does. It reduces the velocity. So here, the force from the damping, it will be in the opposite direction to the velocity factor. Okay, and it will be c omega z naught. Right? So we have c omega z naught. Alright, so we have these three forces of a free vibration system. Alright, so this is basically a free vibration system. So we have already discussed this anyway, so I'm just recollecting so that it becomes easier to follow the next whatever we are going to discuss. Okay, so we have the free vibration system, and for a mass spring despot system. Alright, so this is a mass, so mass spring, so spring and despot system. Okay, so that is the displacement, opposite to the displacement acceleration, and the velocity, which is at a phase of pi by 2. Right? So velocity is maximum at the center, at the equilibrium point. So we have the velocity at the difference of pi by 2. So that is the velocity. So spring force will act opposite to the displacement. If the displacement is in this direction, so spring force will be in the opposite direction. So we have the spring force k naught, k z naught. Okay, so when this spring force will, so the inertial mass, okay, the mass inertial force, it will be in the opposite direction to the acceleration. Okay, so in the opposite direction to the acceleration. So the mass is accelerating in the upward direction. So it will, when the spring will pull it, the spring will get a resistance from the mass. Right, the mass will tend not to change its state of motion. So that is the inertial force. So that is in the opposite direction to the acceleration. So if this is the acceleration, we have this inertial force from the mass. Alright, m into omega square z naught. And when there is a velocity and there is a despot, alright, so this despot, it will always oppose the velocity. Alright, so the force from the despot will be always against the velocity factor. So this is the force from the despot system. Okay, c into omega z naught. Now thing is that, okay, this is maximum displacement, this is maximum velocity, this is maximum acceleration. So this is maximum force, this is maximum, inertial force, maximum spring force, and maximum damping force. Okay, or dashpot force. But then what will happen when it will, the particle, the mass will undergo simple harmonic motion. Alright, the thing is that this entire phase diagram, it will rotate. Okay, and the frequency of rotation will be same as the frequency of the system. Okay, so as it will rotate, so we have this displacement curve with time. We have this displacement curve with time. So displacement will increase and decrease and increase, all right, and decrease, zero and increase. So in this position here, displacement will go move on here, all right, and if we plot it with time, we will get this curve. So as the displacement will change, so also the velocity, but the velocity vector will always be at a phase of pi by 2 or 90 degree. Okay, so when the displacement vector is at this point, so the velocity will be at this point, so the maximum velocity. So here you see we have the displacement at this point and we have the maximum velocity at that point. Okay, and then it will rotate. So as it will rotate, we have this curve, velocity curve with time. We have this velocity curve with time. And similarly, now this is displacement, so the acceleration will be in the opposite direction. So this is the acceleration vector. Okay, so this is the acceleration phase over here, and as the phase will rotate, so also the acceleration value of acceleration. So here you see it is 0, all right, so it is when it is here, so it is 0, so this will be at this point, opposite phase. So here, as the displacement will increase up to this point, so the acceleration will also increase, and opposite to that it will be the maximum at this point. Okay, so this is the maximum, and similarly this is the acceleration curve. Okay, so as we have discussed, so this is displacement, opposite to that acceleration, perpendicular to that velocity, and opposite to this we have the spring force k z naught. Opposite to that we have the inertial force m into omega square z naught, and opposite to velocity we have the damping force or the dashpot force c into omega z naught. Okay, and the values will change as this will rotate, so also this will also rotate. Okay, and similarly here also the forces will vary, all right, with time as the acceleration and the displacement will vary. So we have the equations here. So we have the displacement, so if we differentiate we have the velocity, so in case of sine we have this phase difference pi by 2, and we have the acceleration. Okay, we have the acceleration. So here we can define okay, so suppose now so this is phase diagram for this system. Okay, so now what we do is we have a force, okay, force vibration. So thing is that we have now two motions, one is z1 and one is z2. Okay, so z1 will be moving with the frequency of the applied force, all right, so this omega t which is applied, so that frequency it will maintain and it will undergo this motion. Okay, whereas the natural system, it will vibrate in its natural frequency. So the total force or the total motion that we will have is, it will be z is equal to z1 plus z2. All right, so obviously it will be in the factorial notation. Okay, that you have to keep in mind. So these two motion, it will superimpose. So how to find that out? Okay, how to find that out? So what we will do? So yeah, we have already discussed this. So just for a quick recap, so we have this system. So we have this mass spring system. So we have the dashpot coefficient. All right, and then there is a free vibration. So ultimately, what will happen? So the motion will gradually die out because of the damping. All right, and then we have these two vibrations. So here what we are considering is that there is no damping. All right, the damping is zero. It is zero. Okay, or it is negligible. So we have two vibrations, but in reality, what happens is that the soil natural frequency in the soil or the natural vibrations in the soil, what will happen is that it will die out after a few cycles due to the dampening effect. So this is the natural vibration or the vibration of the natural of the system at a natural frequency. So ultimately it will die out, and what it will be subjected to is the motion which is applied. Now since this is a applied vibration, this will continue to be in motion. All right, it will be continued with time, but the natural vibrations in the foundation system, ultimately it will die out and it will damp out. All right, due to natural dampening of the soil system. But then we have to uh, so what we have to do is, so now what we have to do, so we have this mass and it is acted upon by this force. So we have to, again, as in the previous case, as in this case we have done, so we will again look into the forces which are acting. All right, so we have already looked out. So we have this spring force and we have this damping force and we have the applied force which is F naught sine omega t. So applied vibrating force, and we have the mass. So we have the m into a, the acceleration in the mass. Okay, so similarly, as we made the phase diagram, so here also we can make the phase diagram. So we have the inertial force m into omega square z naught, which we have discussed just now, and we have the spring force which is k into z naught. All right, spring constant into the displacement, which we have just now discussed. All right, so the total force, so we have this k minus mw omega square z naught. Okay, so difference of this force and the inertial force. So we have this resultant. Then again we have the force from the dashpot. Okay, so if you remember, we had the displacement in this direction. So opposite to that we have the spring force, and we have the acceleration in this direction, omega square z naught. So we have the opposite to that, we have the inertial force, and the difference of the two we have k minus omega square into z naught, that is z k naught z minus omega square z naught. So this is the difference, and we have the velocity factor in the upward direction omega z naught. So we have the force in the downward direction c omega z naught. So we have this force. And the applied force, so we have the applied force F naught sine omega t. So basically what it will do at a Steady state, at steady state, it will have a phase difference of phi. So this is the phase difference of phi. So ultimately, F naught, so the displacement Z naught basically will be a function of F naught. Okay, so we will have this force K minus M omega square into Z naught, and we will have this force C omega Z naught, and that will be a result, component of this force F naught which is applied. Okay, so the force F naught, the force applied force F naught, that is, or Q, whatever you see. All right, so in this case it is Q naught, that is the maximum force, maximum magnitude of this vibrating force. All right, that is the Q naught. So that will determine what will be the maximum displacement or amplitude of this system. Okay, and obviously the phi value, will also determine. So if this, there is resonance, so we will see that. Okay, so with the slides we will see that. So thing is that here what we can do, so we can resolve the two components. One is K minus M omega square Z naught. Okay, the other component is C omega Z naught. C omega Z naught. Okay, and we have the force F naught. So this is the force F naught opposing the applied force F naught. Okay, so this is the resultant force F naught which is opposing the applied force F naught. So ultimately we can say that F naught is equal to root over K minus M omega square. Yes, so this is square of this one, so Z naught square actually. So and then we have C omega Z naught square, so Z naught we will take it out, so Z naught. Okay, and then we can, what we can do is, so ultimately we can find out what is the maximum amplitude. So as Z naught is equal to F naught by this term over here, this term over here. Okay, so that is how we can easily and quickly find out the amplitude. In fact, we will apply this. How we will apply this, we will see. Okay, so just keep in mind. So thing is that whenever you get a system of this sort, the first thing that you do is you draw the phase diagram. Very easy. Okay, so we have the force, we have the displacement. So the spring force will always act opposite to the displacement, K naught, K Z naught. So this is Z naught, amplitude of displacement. All right. Then we have the velocity omega Z naught in the a phase difference of pi by 2. And if there is a despot system, so the despot force or the damping force, it will be opposite to the velocity always. All right. So this is the despot force, and when there is a acceleration in this direction, so the inertial force, it will be in the opposite direction to this acceleration. So we have the inertial force. So this is the phase of a free vibration with mass, spring, and despot system. All right. Now, if there is a force, which is acting on that, and it is, vibrating, so we will have another component in this phase diagram of F naught. All right. F naught is the maximum magnitude of the vibrating force. So that will be always opposite to the force from the system. All right. The system will oppose this motion. So that is the, so this is the force from the system, resultant force from the system, and this is the applied force. So action and reaction. Okay, so this is the action and this is the reaction. So the magnitude of Z naught will depend on F naught, and we can find out what is Z naught easily, very easily. Right, so this is A and this is B. Right, so this is C is equal to A square plus B square root over A square plus B square. So that is what we have used here. So very easy to find out. Okay, so the next thing we will continue in the next class.